There is a material sitting in riverbeds, deserts, and construction yards across every inhabited continent on Earth that can absorb heat in summer and release it slowly, steadily, and controllably across an entire winter heating season. It requires no mining of rare elements, no chemical processing, no proprietary manufacturing, no maintenance contract, no replacement cycle. It has been doing this reliably for the entire 4.5 billion year history of the planet, and it will continue doing it long after every lithium battery on Earth has degraded to uselessness. It costs between $4 and $12 per ton. A research team in Finland made headlines in 2022 when they charged a 100-ton sand battery with surplus summer electricity and discharged it as heat continuously across a Finnish winter, one of the coldest and longest heating seasons on Earth, at an efficiency that commercial heating systems costing hundreds of thousands of dollars could not match. The device they used to do it had no moving parts. It did not degrade across charge cycles. It did not require a specialized installation team or a licensed technician to operate. And the core storage medium, the material that held months of thermal energy through a Finnish winter without significant loss, was sand. Ordinary, unremarkable, universally abundant sand that humanity has been building with since the first permanent structures on Earth were raised. The global heating industry generates $240 billion annually. The energy storage industry projects $500 billion in revenue by 2035. Both industries depend on one assumption remaining unchallenged in every building code, every contractor training program, and every government energy policy document written in the last 50 years. That storing heat across seasonal timescales requires expensive, proprietary, infrastructure-scale technology that individuals and communities cannot build, own, or control themselves. That assumption is false. It has been false for thousands of years, and the civilizations that understood it built heating systems from sand and stone that outperformed anything the modern heating industry sells you today. This is the story of seasonal thermal energy storage, the oldest heat battery on Earth. And the reason the heating industry has spent half a century making sure you never thought to ask why we stopped using it. Before we go any further, if this is the kind of knowledge that should never have been buried, hit the like button right now and subscribe to Lost Tech Vault. Every video we publish here is a door they spent money keeping locked. Subscribe and ring the bell so you never miss the next one we open. The physics behind sand as a heat storage medium is not complicated. It is in fact so straightforward that its power is easy to underestimate until you encounter the numbers directly. Every material has a property called specific heat capacity, the amount of energy required to raise 1 kilogram of that material by 1 degree Celsius. Water has a specific heat capacity of 4,186 joules per kilogram per degree, which is why it is used in hot water heating systems globally. Sand, specifically quartz sand, the most common variety on Earth, has a specific heat capacity of approximately 830 joules per kilogram per degree. Lower than water, yes, but sand has properties that water cannot match in a seasonal storage application. Sand can be heated to temperatures exceeding 500 degrees Celsius without phase change, without pressure buildup, without chemical reaction, and without any containment requirement beyond a thermally insulated vessel. Water in a pressurized system becomes dangerous above 100 degrees Celsius. Sand at 500 degrees Celsius is simply hot sand, sitting safely in an insulated container, holding an energy density that at practical storage volumes delivers months of residential heating without a single moving part, a single chemical reaction, or a single utility bill. A cubic meter of sand heated to 500 degrees and insulated effectively holds approximately 100 kilowatt-hours of thermal energy. A well-insulated Northern European home requires roughly 15 to 20 kilowatt-hours of heating energy per day through winter. 20 cubic meters of sand, a storage volume the size of a small garden shed, holds enough thermal energy to heat that home for 100 days without any supplemental input. 100 days, from a shed full of sand. This is not theoretical. This is documented thermodynamics that any physics undergraduate can verify in an afternoon. The ancient world understood thermal mass storage intuitively, even without the mathematical framework to describe it precisely. The evidence is architectural, and it spans every civilization that faced a serious winter heating challenge. The Roman hypocaust system, underfloor heating used in villas, bathhouses, and public buildings across the empire, was not primarily a heating system in the modern sense. It was a thermal mass charging system. Hot gases from a wood fire circulated beneath a thick stone floor and through hollow walls, charging an enormous thermal mass that then radiated heat into the occupied space continuously for hours after the fire was extinguished. The stone and ceramic tile comprising the hypocaust floor held enough thermal energy from a single firing to maintain comfortable interior temperatures through a cold night without any additional fuel input. Roman engineers understood something that the modern gas furnace erased from residential heating culture entirely: that the goal of a heating system is not to generate heat continuously, but to store heat efficiently and to release it slowly. A gas furnace generates heat on demand and stops the moment the thermostat is satisfied. It stores nothing. Every British thermal unit it generates either heats the space immediately or is lost. It is the least efficient possible architecture for managing thermal energy across time. The Finnish, Estonian, and Russian masonry heater traditions took the Roman thermal mass principle and refined it across centuries into what many building scientists now consider the most thermally efficient residential heating device ever built at scale. A traditional Finnish tuulikivi, a massive soapstone or masonry stove weighing between 1 and 5 tons, is fired intensely for 2 to 3 hours once or twice per day. The stone mass absorbs that intense heat and radiates it gently and evenly into the living space for 12 to 24 hours afterward. A single firing consumes a fraction of the wood that a conventional fireplace burns to produce the same heating output, because the thermal mass captures and stores energy that a conventional fireplace sends directly up the chimney. These were not primitive solutions waiting to be replaced by something better. They were sophisticated thermal engineering solutions that the fossil fuel heating industry replaced with something more profitable. The Finnish sand battery that made headlines in 2022 was built by a company called Polar Night Energy in the town of Tampere. The system stores 8 megawatt-hours of thermal energy in a 100-ton sand reservoir heated to temperatures between 500 and 600 degrees Celsius, using surplus electricity from the regional grid, electricity that would otherwise be curtailed and wasted during periods of excess renewable generation. That stored heat is then discharged as district heating for the local community across weeks and months as needed. The round-trip efficiency of the system, energy in versus usable heat out, exceeds 99% across storage periods measured in months. Not days, months. Lithium-ion battery storage systems lose between 15 and 20% of stored energy to heat dissipation over the same period. Pumped hydro loses between 20 and 30%. The sand battery loses less than 1% per month because heat stored in a well-insulated mass moves slowly, and sand-insulated effectively loses energy only at the rate that insulation permits, which, with modern insulation materials, is almost negligibly slow. The Polar Night Energy system cost approximately $10 per kilowatt-hour of storage capacity to build. Utility-scale lithium-ion battery storage costs between $150 and $300 per kilowatt-hour. Grid-scale pumped hydro costs between $50 and $150 per kilowatt-hour. The sand battery costs $10 per kilowatt-hour. Of storage capacity measured in months rather than hours. The global energy storage industry is projecting $500 billion in revenue by 2035, built almost entirely on lithium chemistry, vanadium flow batteries, and pumped hydro, technologies with cost structures between 5 and 30 times higher than sand thermal storage per unit of energy stored. The difference is not technical performance. The difference is that sand cannot be patented, cannot generate recurring revenue from proprietary replacement components, and cannot be controlled by any corporation on Earth because it is the second most abundant material in the planet's crust. What happened between the Finnish masonry heater tradition and the gas furnace monoculture that replaced it is not a story of technological improvement. It is a story of business model replacement. In 1940, the majority of northern European and American homes heated by wood, coal, or masonry systems that stored thermal energy in physical mass. By 1970, the majority of those homes had been converted to gas or oil systems, delivering heat on demand through sheet metal ductwork with zero thermal mass and zero storage capacity. That conversion was not driven by consumer preference research or independent energy efficiency analysis. It was driven by the most aggressive infrastructure build-out in residential energy history, natural gas distribution networks that required captive customers at the end of every pipe to justify their capital cost. The gas utilities that funded that infrastructure build-out needed thermal mass heating to die. A homeowner with a 5-ton masonry heater does not need a gas connection. A community with a sand battery does not need a utility. And what does not need a utility does not generate the quarterly revenue that $240 billion heating industries require to exist. So the building codes were written to discourage masonry mass. The contractor training program stopped teaching thermal storage design. The architectural schools graduated generations of designers who understood BTU output but not thermal mass behavior. And the sand sitting in every riverbed on Earth continued holding heat patiently, the way it always had, waiting for someone to remember what it was capable of. The Romans charged stone floors with heat and slept warm through cold nights 2,000 years ago. Finnish craftsmen refined masonry thermal storage into a heating technology so efficient that modern building scientists study it with genuine admiration. Polar Night Energy built a sand battery in Tampere that stores months of heat at $10 per kilowatt hour and loses less than 1% per month, outperforming lithium storage on every metric that matters for seasonal heating applications. And the $240 billion heating industry continued selling gas furnaces with zero thermal storage capacity to homes sitting above riverbeds full of the most patient heat battery ever discovered. The sand is still there. The physics has not changed. The Finnish masonry heater still works exactly as well as it did 3 centuries ago. And the Polar Night Energy data is publicly available to anyone willing to compare $10 per kilowatt hour against the $150 to $300 per kilowatt hour that the energy storage industry needs you to believe is the only viable option. Your heating bill is not a law of nature, it is a business model. And the material that could replace it has been sitting in your nearest riverbed, completely free, since before the first human being ever felt cold. Subscribe to Lost Tech Vault. Share this with someone paying a heating bill that a shed full of sand and 2,000 years of documented physics already solved. The next vault opens soon, and what is inside it is heavier than this one.